In this video, I will present some of our recent work on what we call the angular blowing a kiss problem. The angular blowing a kiss problem is as follows. Consider n agents in the plane, each equipped with an orientation. The position of these agents is fixed, but they can rotate to change their orientation like this. When two agents are oriented towards each other, they are able to scan each other. We indicate this with a red line. The question we are interested in is the following. How long does it take to scan all pairs of agents? One way to illustrate this problem is the following scenario. Suppose a group of friends wants to say goodbye to each other and wants to do so by blowing kisses from where they stand. How long does it take for everyone to say goodbye to everyone else? A more practical application that inspired this research is a project by NASA to scan the Earth's magnetosphere with satellites. To do this, the directional antennas of the satellites have to be oriented towards each other. There are several related problems. The name blowing a kiss problem is inspired by the kissing problem. In this problem, the agents move around and scan each other when they are close. Like our problem, the angular freeze tag problem also deals with rotating agents at fixed positions, but there the agents do not have to be looking at each other to communicate. In our problem, we scan all pairs of agents, which is the same as scanning all edges of the complete graph of these agents. Fekete, Kleist, and Krupke consider this problem for graphs other than the complete graph. I will now give some more details about the problem. First, we will only consider the rotation time of the agents, which takes time proportional to the angle of rotation. Our goal is to find a schedule that scans all pairs of agents and that minimizes the makespan, or in other words, the total time needed until all pairs are scanned. For example, even though all agents in the figure spent only pi/3 time rotating, the total makespan is 2 pi/3, since agents spend some time waiting for the other agent to look at them. We distinguish synchronous and asynchronous schedules. A synchronous schedule consists of n or n-1 consecutive rounds, with each round having n/2 rounded down simultaneous scans per round. For example, the configuration on the left is part of a synchronous schedule, since all but one agent are participating in a scan. The configuration on the right is not, since it has two agents not participating. Any schedule that is not synchronous we call asynchronous. Here you see our results. We investigated this problem for 3 different configurations of agents. The 1D case where all agents are on a line, the case where all agents are uniformly distributed on a circle, and finally arbitrary positions in 2D. The top row indicates the time required for the best schedule we are able to construct. The middle row indicates the time for which we can find a schedule if we require it to be synchronous. The bottom row shows the lower bounds we have found in this setting. In particular, we can find optimal schedules in 1D and constant factor approximations in the uniform circle case. In this video, we will take a closer look at the algorithms to create synchronous schedules. We first look at the case when all agents are uniformly distributed on a circle. We show a synchronous schedule for the case where n is 2 to the power k for some integer k. We label each agent in counterclockwise order. The main idea is to scan all agents within k phases, where in each phase we scan all pairs where their label differ than the k's bit and have not been scanned earlier. We do this by rotating the agents with a 1 at the k's bit, the 1-bit agents, clockwise, and the other agents, the 0-bit agents, counterclockwise. We show an example for n is 8, where we have 3 phases. In phase 1, we look at the first bit. The 1-bit agents are colored black, the 0-bit agents are colored blue. We scan all pairs of 1 black and 1 blue agent by rotating the black agents clockwise and the blue agents counterclockwise. We are now done with the first phase. To start with the next phase, each agent rotates to the first unscanned agent in the direction of the next phase. Now we scan all pairs we haven't scanned yet and differ in the second bit. Finally, in phase 3, we scan the agents that only differ in the third bit. Within a phase, an agent rotates at most by an angle of pi. To restart for the next round, it again rotates at most by an angle of pi, and since there are log n phases overall, the overall time the schedule requires is at most 2 pi log n. Next, I present our algorithm to construct a synchronous schedule when all agents are on a single line. The main idea is to iteratively construct a schedule Sn by applying the following rules, which I will describe later. First, note that if we have only 2 agents, there is a schedule which takes 0 time, as you can see on the slide. Rule 1. If we have a schedule for k where k is even, we can construct a schedule for k minus 1 which takes the same time. Rule 2. If we have a schedule for k, then we can construct a schedule for 2k which takes an additional pi time. Note that with these rules we can construct a schedule for any n. If we apply these rules to reach Sn from S2, we need at most log n over 2 applications of rule 2, since this is the only rule that increases the time required by the schedule. The total time of the schedule constructed this way is pi times log n minus 1. Next, I will explain how we construct schedules with rule 1 and 2. With the first rule, we can construct a schedule for k minus 1 agents if we are given a schedule for k agents with k even. Consider some round I of Sk. Since k is even, each agent is scanning some other agent. In particular, there is an agent scanning the last agent, agent pk. We now construct the schedule for Sk-1 by removing the agent pk from every round and make the agent that was scanning pk a bi-agent. Note that this is still a synchronous schedule because k-1 is odd. It also takes the same time since we do not change the orientations of the agents. Additionally, observe that the bi-agent in each round is oriented toward the right since it was originally looking at pk, the rightmost agent. For the second rule, we show how to construct a schedule for 2k agents when given a schedule for k agents. For the first half rounds, leftmost k points follow the schedule of Sk, and in parallel, the rightmost k points follow the schedule for Sk, but then with all orientations and scans horizontally mirrored. If k is even, these are all synchronous rounds. After these rounds, we have scanned all pairs where both agents are in the same half. However, when k is odd, schedule Sk and its mirror both have one bi-agent not participating in a scan. Note that schedules for odd k are constructed via rule 1, where the bi-agent in Sk is always oriented to the right. Since the other bi-agent is in the mirrored schedule, it is oriented to the left, and the two bi-agents are looking at each other. So we can scan these agents to get a synchronous schedule in this case. At this point, if k is even, all that remains is to scan all pairs with one agent in the left half and the other agent in the right half. To do this, rotate all agents in the left half to the right and all agents in the right half to the left. The remaining pairs form a regular bipartite graph, which we can scan synchronously in the final rounds. If k is odd, this regular bipartite graph has a perfect matching removed, so it's still a regular bipartite graph which we can scan in the final rounds. The first rounds of the schedule take the same time as Sk, and the final rounds are done with one rotation of angle pi, so the schedule indeed adds pi time. Now I will show an example of this construction to create a schedule for 6 agents. Start with a schedule for 2 agents. We now get a schedule for 4 agents by first mirroring S2 and running it in parallel. Next we rotate the left and the right half, and scan the bipartite graph between the left and right half. This completes the schedule for 4 agents. Now we get a schedule for 3 agents by removing agent P4. To construct S6, first follow S3 on the left half and mirror the schedule for the right half. Now we match up the bi-agents to get the first rounds of the schedule. Rotate the agents one more time and scan the bipartite graph between the left and right half. This completes the schedule for 6 agents. To recap, we have found optimal schedules for the 1D case and schedules which give a constant factor approximation when the agents lie uniformly on a circle. We are currently working on synchronous schedules that apply to the general case and are investigating the computational complexity of that case. Thanks for watching.